So in this section, we'll look at two different forms of energy, building off of kinetic energy and the work energy theorem, potential energy and total mechanical energy, the topic of 3.2. So we start by defining potential energy, a term you may be familiar with. So potential energy is defined as the energy stored in an object, allowing the object potential, hence the name, to move if an external force acts upon it. So as an example, if we have skiers that are placed up a certain height above the ground, they have potential energy due to gravity. Hence, they have the potential to move if you remove their platform. The idea being is if you remove their platform, an external force, the force due to gravity, acts upon them to bring them down to the earth. So we define this as gravitational potential energy. We represent potential energy with the letter U in physics, and then we use a subscript capital G for gravitational potential energy. So as we just talked about, it's a potential energy due to the force of gravity. Each of these skiers wants to be down on the ground, but they cannot because they have these platforms there. Thus, they have the potential to move and have potential energy stored in them due to the force of gravity. If you remove the platform, the force of gravity acts to bring them back down to the earth. So, with gravitational potential energy, there is a direct relationship between gravitational potential energy of an object and the height of the object. Specifically, that if our skiers are brought to a lower height, they have less potential energy because they have less potential to move. You see this that if they drop from a smaller height, they're going to hit the ground with a lower speed. Whereas if they are dropped from a higher height or ski from a higher height, they're going to reach the bottom of the ground with a higher speed, thus indicating to us that they have a higher amount of energy stored into them if they're at a higher height than at a lower height. And you can just kind of imagine the high heights and low heights in between. So we say the gravitational potential energy of an object is proportional to the height of the object. The equation we subsequently use for gravitational potential energy is gravitational potential energy equals the mass of the object times the acceleration due to gravity times the height at which the object is located. The change in gravitational potential energy also corresponds to a change in height, and this is what you'll see on your equation sheet. Delta Ug, our change potential energy, is equal to mg delta h. And this again corresponds to the idea that if our skier skis down the slope or drops down the slope a certain height, their potential energy is going to decrease because their height is also decreasing. And we can also see this relationship that our blue skier has a higher potential energy since they're a higher height than the yellow skier right here. Just a brief little synopsis of everything that we have covered so far. So the big thing with potential energy is potential energies, whether gravitational or otherwise, possess a quality known as path independence. So potential energy of any type is path independent, meaning that only the initial positions matter for the potential energy, not the path taken in between to get from the initial to the final position. So, as an example, an object that ends up at a height h will have the same gravitational potential energy regardless of the path taken to get to the height. So if we start out at A and we lift up our object at height h to B, that object will have the same potential energy as their height is the same regardless if they take the green path, the red path, or the blue path to get to B, as regardless of the path taken, they all end up at the same height h. I'll give you a second to write that down, or pause if you need be. Lastly, we arrive to what's called total mechanical energy. Total mechanical energy is labeled by the letter E. It denotes the energy that can be used for work by the system, meaning that it can be taken out of the system and put into a system to allow the object to move, either by slowing down the object or speeding up, as we saw what work does. It is defined as the sum of all the potential energy U and all the kinetic energy K of a system. So, and this isn't on your equation sheet, but this is an easy equation to remember. The total mechanical energy is equal to our potential energy plus kinetic energy. So as an example, when a car is in motion, a car stores potential energy in its gas tank in the form of chemical bonds in the gas molecules. Okay? So this is considered this gas molecule, these gas molecules, is considered a part of the total mechanical energy because the potential energy in chemical bonds can be used for work by the car engine to propel the car forward. Specifically, what happens is the potential energy in chemical bonds is converted to kinetic energy by the engine. The engine does work that converts the potential energy in chemical bonds to kinetic energy, which allows our car to move. Hence the idea of total mechanical energy. Kinetic energy and potential energy can be converted back and forth to increase or decrease the motion of our car through work done by the engine. Specifically, if we want to slow down our car and decrease kinetic energy, we'd have to apply brakes to the car. And these are two main concepts for potential energy and total mechanical energy.